Welcome to this explainer. Have you ever watched two things crash into each other? Maybe pool balls cracking together on a table, or even just cars in a fender bender, and wondered exactly how the universe decides what happens next? Well, today we're exploring the absolutely fascinating and honestly sometimes totally non-intuitive world of physics collisions. We're going to unlock what is literally a mathematical cheat code that physicists use to bend these incredibly complex mechanics completely to their will. To kick things off, I want you to picture a famous experiment from Professor Walter Lewin's MIT physics lectures. Imagine a heavy, solid billiard ball plowing straight into a tiny, super light ping pong ball. If you sit down and actually do the math on this, the ping pong ball shoots off at exactly double the initial speed of the billiard ball. But why? And how does physics solve this interaction in the absolute blink of an eye? Okay, let's dive into this because, as Professor Lewin so wonderfully points out, nature doesn't exactly sit around with a graphing calculator trying to solve complex algebra, right? It just effortlessly follows these fundamental laws of conservation. And to understand how nature calculates this instantly, we really have to look at how we're framing the problem in the first place. Now, before we solve our ping-pong paradox, we kind of need to establish the ground rules here. In physics, there are basically two extremes when things collide. On the one hand, we have perfectly elastic collisions. This is where kinetic energy is fully conserved. Nothing is lost, kind of like ideal, magical billiard balls bouncing perfectly off each other. Then, on the other end, we have perfectly inelastic collisions. That's where objects crash, completely stick together, and a bunch of kinetic energy is just permanently lost from the system. Here's the catch. If you try to calculate these collisions from where we're sitting right now, what physicists call the laboratory frame, it is an absolute nightmare. Seriously, you're forced to wrestle with these huge, complicated quadratic equations just to figure out the final speeds of the objects. It's a tedious mathematical chore, it's incredibly messy, and frankly, it's just exhausting. But what if I told you there's a better way? Enter our physics cheat code, the center of mass, or CM frame. Think of this as a moving reference frame that is tied directly to the invisible center of mass between the colliding objects. And the absolute magic property of this specific frame? The total momentum of the system inside it is always exactly zero. Now, what's really interesting about this view is how completely the math transforms. Take this elastic collision of a spring block setup, for example. In our normal everyday lab view, both blocks are moving at different speeds, which complicates literally everything. But from the CM view, because the system's total momentum is zero, that single massive momentum conservation equation splits perfectly into two incredibly simple equations. It's beautiful. I actually want you to try a little Jedi mind trick with me right now. Picture these blue and red balls approaching each other directly. I want you to imagine you are literally sitting on that invisible center of mass between them, moving right along with it. From your new perspective, you are completely stationary. All you see is both particles traveling directly towards you with equal but opposite momentum. And because of this brilliant zero momentum rule, we can use a super simple three-step process to completely bypass all those nasty quadratic equations. Ready? Step 1. Subtract the velocity of the center of mass from your objects so you can enter the frame. Step 2. Calculate the bounce. And step 3. Just add the CM velocity back to return to your normal lab frame. That's the whole shebang. And here's the best part. Step 2 is beautifully simple because of the golden rule of elastic collisions in the CM frame. Particle speeds remain exactly the same. Their velocity vectors simply flip direction. Because total momentum absolutely must remain zero and kinetic energy is conserved, the particles just bounce back the exact way they came. They approach you and they bounce directly away from you at the exact same speed. So let's bring back our opening hook, right? What actually happens when a heavy billiard ball plows into a tiny ping pong ball? To put that into perspective, this is a massive weight difference. We're talking a ratio of about 500 to 1. Let's go ahead and apply our brand new center of mass cheat code to see exactly how nature handles this real-world setup. Let's start with the obvious, intuitive scenario: bouncing the ultralight ping pong ball off the stationary, heavy billiard ball. Because the billiard ball is just so incredibly massive, the center of mass is basically sitting entirely inside it. So the ping pong ball comes in and hits it, the heavy billiard ball practically ignores the impact entirely, and the light ping pong ball just bounces back with almost its exact initial speed. It's literally like bouncing a tennis ball off a solid brick wall. But here is the non-intuitive paradox. When the heavy billiard ball hits the stationary ping pong ball, the center of mass is actually moving with the billiard ball. From that moving CM frame's perspective, the ping pong ball comes flying at it, bounces perfectly, and flies away. When we do step 3 and add the moving CM frame's velocity back to return to our lab frame, the math dictates the ping pong ball must fly off at exactly twice the speed of the billiard ball. And this brilliantly illustrates the wild, yet completely mathematically perfect conclusions we can draw just by using this perspective shift. Let's move to and see how this builds when things don't bounce perfectly but instead crash and stick together. We're officially shifting from elastic to inelastic collisions. This is famously demonstrated in physics labs using sticky carts gliding toward each other on a frictionless air track. In our standard everyday lab frame, if two sticky carts hit each other, they'll just continue sliding together at some new, slower speed. But in the center of mass frame, when two particles stick together in a completely inelastic collision, they stand perfectly still. Think about the logic there for a second. They kind of have to. The total momentum in the CM frame must always be 0. So if they're literally stuck together, the absolute only way to have 0 momentum is to not be moving at all. So the crucial point is this. Before the inelastic collision happens, there's maximum kinetic energy present in the center of mass frame as the objects are flying toward each other. But after they crash and stick, well, because they have to stand perfectly still in this frame, the center of mass kinetic energy drops to absolutely 0. 100% of the kinetic energy within the CM frame just vanishes. Poof. But wait a minute, we know energy can't just magically disappear from the universe, right? So where does all that lost kinetic energy actually go? Well, it physically transforms. It goes into the actual deformation of the objects. Think of a piece of putty flattening against a wall or the metal crunching in a car crash. A bunch of it is emitted outward as sound waves that you can hear. And crucially, it's converted into internal thermal energy, literally heating up the objects and diffusing out into the surrounding environment. We've covered some genuinely amazing concepts in this explainer today, and they were entirely unlocked just by shifting our perspective away from the lab and onto the center of mass. Before we wrap up, I want to leave you with Professor Lewin's famous 3 a.m. sleepless night challenge. Imagine a tennis ball bouncing perfectly elastically off a massive, solid, rigid wall. We know it comes back with the exact same speed. But if momentum absolutely must be conserved in the universe, what really happens to the momentum here? Think about it. Try applying your new physics cheat codes and let that question spark your curiosity until next time.